what does this show? The two arbitrary partitions. Once the mesh or the norm of the partition is less than delta that's required to keep the function variation less than epsilon on every subway. The Cauchy sums over any two of them are never more than 2 epsilon times b minus a and 1. We can control epsilon by picking ever smaller deltas and using uniform probability. 2 is fixed, b minus a is fixed. We can control that entire difference, right? So the game is, once you get small, if there's anybody else out there that's equally small, you're never more than this apart, right? That's what we've established. All right, that's a huge result, because now what we'd like to do is show that if I have a continuous function, I can make sense and define the Cauchy integral. And how's that defined? The Cauchy integral from a to b of the continuous function f of x dx is equal to the limit as the partition norm goes to 0 of the sum equals 1 to n, determined by the partition, of course, f of xi minus 1 xi minus x. So that's our definition. We would dearly like to establish that that limit exists. And here's how we do that. You see why we make such a fuss over uniform continuity? It allows us to establish the lemma, the technical lemma, that the difference between any two Cauchy sums, once the partition mesh is a certain size, is controllably small. Right? That was the lemma that we used. Because now I'm going to take a particular sequence of partitions, and after a while, they're going to get small. And hence, anything that's as small as them will never be more than epsilon, 2 epsilon times b minus a away from them, right? And if that's true, then everybody has to be, once you're arbitrarily close to something that is approaching a limit, you're approaching that limit too, right? Right? Okay. So what shall we take as, I would like to have a sequence of partitions, and that will induce a sequence of sums. And if I can show, using my lemma, that that sequence is a Cauchy sequence, then by completeness of the reals, I will have a limit, right? We went to some trouble last week to show that. Remember, in the reals, a Cauchy sequence converges. Convergent sequences are Cauchy. Cauchy sequences are convergent. In the general case, convergent sequences are always Cauchy. But Cauchy sequences may not converge, right? In the rationals, sequences of rationals, if they converge, they're Cauchy. But Cauchy sequences and rationals, as we know, don't necessarily converge. They can, and maybe they don't, right? If they're looking for one of the holes in the rationals, then they don't converge. Okay, so let's do this. Let's set P1, let's set P1 to be this. X0 is A, X1 is B minus A over 2 to the 1. Xk is K times B. Sorry. Well, X2 and B. How's that? That's not a very big one. P2. X0 is A. X1 is B minus A over 2 squared. X2 is B minus A 2, B minus A over 2 squared is B minus A over 2. X3 is 3/4 B minus A, X4 is B, right? B, Humpty Dump here. X0 is A, X1 is B minus k over 2 to the k, right? And then x sub 2 to the k is b. Okay, so I have a sequence of partitions here. What's the norm? What's the norm of this partition, Amanda? This one, b sub k. What's the norm? Well, how big are these subintervals? They step along the same. You know, I'm dividing b minus a by 2 to the k. So I have 2 to the k subintervals, each of length b minus a over 2 to the k. So what's the norm? You would say it is b minus a over 2 to b.
I'm still on partition.
What's that? Okay, we're still one page behind. All right.
We're trying to figure out what that last thing says.
X to the 2k,
No,
and
above
x sub
that.
2k.
X up above it.
X sub 4.
Ah.
Is my writing that bad? I'm sorry.
No, I think it's the pen is a little bigger tonight.
Okay.
So. No, it is. You get those points.
Betrayed by thick pen. All right. So I have these partitions marching along, and the norm, the lim, as k goes to 0, sorry, k goes to infinity,
The norm is x1 in all cases.
p sub k is 0, right? Yeah, x1 minus x naught is the same as x2 minus x1. It's the limit of some finite amount over 2 to the k for arbitrarily large k. That's going to be, so as k gets bigger, the norms get smaller. Now, what did we just show? Once, okay, you pick an epsilon, then you can find a delta from uniform continuity, such that once the norm of the partitions gets below delta, any two partitions with mesh no greater than that differ by at most 2 epsilon times b minus a. Isn't that what our lemma was? Technical lemma. Well, look, these guys are headed off to 0. So you pick an epsilon, and then I will find the delta such that once the norm of anything is less than that, any two partition sums, the sums based on any two partitions satisfying this inequality here are never more than 2 epsilon times b minus a apart. Okay? Let's call that epsilon apart. Right? We can do that. So I can make the difference in sums arbitrarily small by just picking epsilon really small. Right? Yeah, so I multiply it by 2 times b minus a. I can absorb that with my epsilon prime. So what are we saying? Once you get past delta with the norm of a partition, any two partitions after that induce sums that are never more than epsilon prime. That sounds to me like it's Cauchy, doesn't it? What's a Cauchy sequence again? A Cauchy sequence xn is one that once any two indices get past a certain point, so n and m greater than the magic n, this difference between them is arbitrarily small for any n and m, right? Don't I have that? If you tell me, keep the sum, the Cauchy sums, be lower than epsilon prime, I will go find the corresponding epsilon, go find the delta, and then once my partitions are smaller than that, this condition will be true, right? For epsilon prime instead of epsilon. Right?
Where your xn's are your summations? Or?
Yeah, this would be a sum using one partition. This would be a sum using the other partition. They would be less than the epsilon prime. Well, I I need to be able to find n's and m's. But look at what these partitions are doing. All right? Once you get past a certain point, you tell me what delta is, and I'll get past it. Right? How do I get past it? I just make sure that b minus a over 2 to the k is less than delta. So b minus a over delta is less than 2 to the k. Take binary logs of both sides, and that's a condition on k. So k has to be greater than the binary log of b minus a over delta. Binary log is log to the base 2, right? So what do I have? I have a Cauchy sequence of solids. So it converges. And like the monotone convergence theorem, this is a way that you can plot the limit on it. You can justify the existence of a limit.